For this video, we are tasked to identify the three reflections of our point x, which is 5, 0, along the lines alpha, beta, and theta here. Now, to do this, let us try to plot this first, the point on our Cartesian plane. Since we have here our Cartesian plane here, considering that all grids are 1, so we could have here our x is at 5, 1, 2, 3, 4, 5 is 0. This is our x, 5, 0. Then we are going to take its three reflections following this given here or item. We have here beta, theta, alpha of your x. Just by looking at this, we understand that it would start by reflecting to alpha, then the reflection will be reflected to theta, and then its reflection would be reflected to beta to identify the three reflections. Okay, we can do that, but of course, there is another method for us to determine the three reflections in a shorter, in a more comprehensive way. We use here as a combination of a reflection and then a translation. Hence, we will be using the concepts we have learned before, especially the formula for reflection and translation. Before we start, I would like to graph these three lines here. If you don't want to see this one or watch this or view this one, you can always skip the video to the point of the process already on you getting the reflection first of our point x along line alpha. But for me to be able to understand the entire concept of the reflection, I'll be plotting this, graphing these three lines here. And to graph that, of course, we're going to use the intercepts. As for alpha, identified by x plus 2y equals 4, when we let y equal to 0 to get our x-intercept, we can have here x plus 0 equals 4. So x is equal to 4. That's our x-intercept at 4 and 0. For our y-intercept, let x be equal to 0. So we have 0 plus 2y equals 4. 2y is 4. And then y is 2. So its y-intercept is at 0 and 2. Allow me to continue getting the intercepts of the remaining lines before plotting them on the Cartesian plane. So let's proceed to the next line, which is actually the beta. Beta is x plus 2y is equal to negative 4. Okay. So with this, for our x-intercept, let y be equal to 0. X plus 0 is negative 4. So x is negative 4. Our x-intercept is at 4 and 0. Then we let x be equal to 0 to get the y-intercept. So you have 0 plus 2y equals negative 4. So you have here 2y is minus 4. So y is negative 2. So our y-intercept is at 0 and negative 2. Now for our theta, which is actually a line here, not an angle. So you have here x plus 2y equal to 0. So for our x-intercept, let y be equal to 0. So we have here x plus 0 is 0. So x is 0. That would mean our x-intercept is at 0 and 0. Now obviously, since our x-intercept is at the origin, that is also our y-intercept. If you're not convinced with that, of course you can continue by letting x be equal to 0. So you have here 0 plus 2y be equal to 0. 2y is 0, so y is 0 as well. So similar to that. In short, we have 1 point here. But since we need 2 points to draw a line, allow me to choose another value if x is equal to 1 so that we could have another point on this line in order for us to graph that, because then again, we just need at least 2 points to determine a line. So if x is, let's not use 1. Okay. You may use 1 if you would like to, of course, but I was thinking of using an even number because we have here even coefficient. But either way, if x is 1, you have x 1 plus 2y equal to 0. 2y is negative 1. So we have here y is negative 1/2. This is neither x-intercept nor y-intercept, but it's another point on theta which will allow us to graph that. Since we have all of this already, let's try to graph this on our Cartesian plane. For our alpha, our x-intercept is at 4, 0, and then it's at 0 and 2. So if we're going to connect it with the line, assuming that I could connect it in just one attempt. Sorry, let me do it again. I was thinking of the other point. Let's just assume that I had that. So this is actually our alpha. Okay. Now for our beta, it's actually -4 and 0. So we'll have here 1, 2, 3, 4. That's -4, 0, and 0, -2, 1 and 2. So it's here. So if we're going to connect this one, we would expect that the line is parallel to the first line drawn. That is because they share the same slope. Let me do it again. Okay. Okay. They share the same slope. This is beta. Why do we say it? We share the same slope. Take note of the coefficients here. Our A is 1. Our B is 2, which is also true for this, and of course true for our theta. This means that all of these three are actually parallel. To graph the remaining line, we know that it would pass through the origin. So we have here our origin, and then at 1 and -1/2. So if I may, 1, -1, -1/2 somewhere here. So again, if I'm going to connect that, hopefully I could come up with still a parallel line, assuming that this is already okay. So we can still see here that it is actually parallel. And in this case, we can now see clearly that this notation is actually correct, as to get the three reflections, we are to reflect first x by alpha. So this is alpha, the closest line. So obviously we can reflect it here, and the said reflection will be reflected to theta, which is actually our second line. Okay? And then later on to beta, our third line. This supports the idea that we can actually solve for the three reflections for our point x. Now, hopefully you were able to understand the graphing portion, because this time we are not to solve for the intended output. Take note that we can start here by combining or solving first the reflection of x along our line alpha. Of course, again, you can work on three reflections, repeat them, but I'm going to use here the reflection and then the translation. So allow me to focus first, on the reflection of x along alpha. We know that x is actually identified as 5 and 0. For any reflection, please don't forget that we have a formula, x minus twice the inner product of x minus p in the unit normal vector times the unit normal vector. Our x is of course given here. Our point P is any point on alpha. How about our unit normal vector? That's the thing that we need to solve here. So we know that our normal vector has composition of A and B, and since we have the same A and B for all, we can use that. So our normal vector is at 1 and 2. Take note that the normal vector of our line alpha is also the normal vector for our line theta and beta, because we know that all these three lines are parallel. That would mean if we're going to draw here, just for an example, a normal line which is perpendicular to one, it will also be perpendicular to the other two. Hence, the normal line having a direction vector of a normal vector is true for all. Okay? So later on, if we're going to use the same unit normal vector for another problem or under other concerns, specifically for the translation portion, then we are going to use the same unit normal vector. Now, for this, we need to identify our unit normal vector. So first, let's take the length of our normal vector. It's actually the sum of the squares and the square root of that. So you have here 1 plus 4, so square root of 5. But our normal unit normal vector, normal vector is actually the ratio of your vector using parentheses. Don't be confused with that. We can also use parentheses for a vector. Don't be confused with that as a point. That's a vector. But this time, let's use parentheses just to illustrate our unit normal vector over square root of 5. Or you can actually use here this one, 1 over square root of 5 and 2 over square root of 5. So this is our unit normal vector, which is true for our alpha and at the same time for our theta and beta lines. Okay. Now, let's return to this one here. Take note, we'll be using P Now, to be consistent to what we did in the previous videos and so on, and later on as well, if we are to pick a point on a line, as long as it is available, let us use the x-intercept. Now, of course, you can use the y-intercept. You can even use x-intercept later on. You can exchange them. But as long as you will be using the correct pairs, especially for translation or the foot of perpendicular, it's okay. But just to be consistent, allow me to use the x-intercept for 0. So that's what we're going to use here. Our p being 4 and 0. So for this, our x is actually 5, 0, minus twice the inner product of, 5, 0, minus our p, which is 4, 0, with the unit normal vector, 1 over square root of 5, 2 over square root of 5, still to be multiplied with the same unit normal vector. Okay? So let's do this step by step, and I might be using another page here because this is just the first part, the first reflection. So you have here 5, 0, minus twice. Of course, you can combine the first, the 2 points first. You'll get here 1, 0. And that is actually the result. 5 minus 4 is 1, and 0 minus 0 is 0. You have here 1 over square root of 5, 2 over square root of 5, times again 1 over square root of 5, and 2 over square root of 5. To continue, you have 5 and 0 minus 2. And of course, for inner product, simply multiply the corresponding components and add them. Take note that the result here would be scalar. So 1 times 1 square root of 5 is just 1 over square root of 5. And 0 times the other is just 0. So we just simply have it something like this. So your unit normal vector would still be continued here. So here we have here 5 and 0. By multiplying the scalar, you will have here 2 times 1 times 2. So you can actually get here, this is minus. So you have here 2 over the denominator would be rationalized. Square root of 5 times square root of 5 is actually 5 or 2/5. And then for our second, you will have 2 times 1 times 2 here is actually 4. So you have 2 times 1 times 2 is actually 4. Sorry for that. 4. And the denominator is still 5. Okay. So for this, the reflection of x along line alpha is identified by 5 minus 2/5 and 0 minus 4/5. So you will have here a result equivalent to, you may use your calculators there if you would like to. So 5 minus 2/5 is actually equal to 23/5. As for the second, since it's just 0, so negative 4/5. This is still the reflection of x along line alpha. If you would like to continue with the 3 reflections, reflect this into the second line, which is theta rather, and the result will be reflected to beta, and that the final result will be their 3 reflections. But this time, allow me to use translation. Okay, because as I'm done with the first reflection, I'll be using that reflection for a translation. So I'll be using here another page. Allow me to use this page here. So if I'm correct to remember, we have here the reflection of x along alpha is actually 23/5 and minus 4/5. Allow me to check it if it's correct. Okay, and then take note that what we're trying to solve for is this form. Okay, theta and then alpha x. This means this is already identified as that. So if we're going to let the reflection of x along alpha be another variable, let's say y, this would mean that this could be written as the reflection beta, theta, and you have here your y, which would actually be representing translation. So we're going to translate y along theta, and to solve that, we have the formula here in this manner. The formula is expressed as x plus twice p minus q. Okay, but take note, since we are using y now as the reference, which is equivalent to a reflection of x along alpha, allow us to erase this and change it to y. Okay, so what we need to do here is just to identify what would be our p and q. Take note, p here is not similar to the p we used earlier as 4 and 0 in solving for the first reflection, because that's actually the point on the first line alpha, and specifically it's its x-intercept. This time, we will not be using P as an intercept because P is actually the foot of perpendicular on connecting here. What would be the farthest line? It's actually beta. So we have here on beta using a certain Q on, if we're going to have here its reflection, the next line is actually theta. Okay? So that means we're still going to solve for P, and P is not just any point, it's specifically a foot of perpendicular using Q. Looking back on our graph, take note that we can pick here any Q because it is composed of infinitely many points. And as soon as you pick any point there, you can simply take the perpendicularity on our next line, and that would be your P. Of course, if we're going to pick this point here, this would be your P here. So in short, P is dependent on your Q. To do this, to be consistent with what we did, the first thing we need to do here is to identify the Q. And again, it would be a point on theta. And this time, allow us to use the x-intercept to be consistent. Of course, that's also the y-intercept, so it doesn't matter as long as we choose that. And at the same time, you would see it's a combination of two zeros. Whenever it's possible for us to choose any point that will be integrated in our formula which contains zeros, do that, because later on, when you're going to introduce that in the formula in this manner, it's easier to do that, even if it's under what do you call this one, an inner product or other formula. It's easier for us to handle zeros. Now, since we are done with our Q, let's identify our P. Our P again is the foot of perpendicularity using Q. Take note of the formula for F, or foot, in this case P, is actually x minus the inner product of x minus P times unit normal vector, and we have your unit normal vector. Take note, the x here is not the given x earlier. It would be the reference point on our theta that we are using, and that's this point here. So when we try to revise this formula, it would be our Q, and Q minus, again, the P is not the P we used here earlier, nor the P we're talking this one, because that's what we're trying to solve. P here is actually any point on our third line beta. So again, to be consistent, let's use the x-intercept of our beta, negative 4 and 0. So you will have here, let me use, again, it will be the intercept on our beta times the unit normal vector here. And the unit normal vector is the same as this value here. Okay, take note of that. We'll be writing that here. So our x-intercept for our beta is actually identified as negative 4, 0. And the unit normal vector is 1 over square root of 5. And you have here 2 over square root of 5. So for all of this, we can now solve for our P intended for the translation or the foot of the perpendicular on our beta using our Q on theta. So you will have here, sorry, this is minus again. So this should be minus, right? Anyway, so let's try to solve for the foot first. So our Q is at 0, 0. Okay? And then minus, you will have your 0, 0 minus your intercept, which is negative 4 and 0, to be multiplied with your unit normal vector. I mean, inner product of that with unit normal vector, to be multiplied with your unit normal vector outside. Okay? So this is again 0, 0. Minus, the combination of that will be positive 4, double negative property, and 0, and then to be paired with the unit normal vector for an inner product, then the result of that would be a scalar to be multiplied with the unit normal vector outside. So this is 0, 0 minus. So you can see that one item is 0 because that's a the product of that. So you have 4. The first components, 4 times 1 is just equal to 4 over, sorry, this would no longer be inner product. This is just a scalar. So square root of 5 plus 0, so it seems like that, 1 over square root of 5, 2 over square root of 5. Okay? So you will have here 0, 0 So by the first, 4 times 1 is 4. And take note, rationalize the denominator just like earlier. So you have 4 fifths. And you have 4 times 2 is 8. And you have here, sorry, it will be just 5. Since the first point is 0, so we would know that our foot, which is equal to our P intended for our translation here, okay, is actually equal to negative 4 fifths and negative 8 fifths. Okay? Negative 4 fifths and negative 8 fifths. This time, we now have our P. So let's now solve for the final. This actually stands for this one here, the translation for our theta of our y. Okay, this is the point here, translation along line theta is equal to y plus twice p minus q. So our y earlier is actually the reflected point for along a reflected point or reflected image, the image of our x along line alpha. 23 fifths and minus 4 fifths. 23 fifths minus 4 fifths plus twice. Our p is negative 4 fifths. 8 fifths, that's negative, sorry, minus, again, we have here, our q is 0, 0. See, it's easier really to handle points which are zeros. So you have 23 fifths, negative 4 fifths, plus twice, so we have here just itself, because we have 0 as its pair, 23 fifths, negative 4 fifths, plus you have your negative 16 fifths. You have, sorry, that's negative 8, sorry. Negative 8 fifths. And this is negative 16 fifths. Okay? So you would see here that the result would just be equal to 23 fifths minus 8 fifths, or plus negative. And you will have here, the second is negative 4 fifths plus negative 16 fifths, which will give you, that's actually 15 fifths and negative 20 fifths in simplified form. This is actually 3 and negative 4. This again, that which is in general, you have the reflection, the 3 reflections of your x along alpha. For y is equal to the reflection of x along line alpha. So it's a 3 and negative 4. Okay, this is the final answer, and let us try to illustrate that on our Cartesian plane. Negative 3 is actually somewhere here. Sorry, that's positive 3, 1, 2, 3, and negative 4, 1, 2, 3, and 4. This is here. This is its 3 reflections, beta, theta, alpha of your x. Okay, so it patterns from the reflection here and in the translation. Or if you would like to use another reflection here to be consistent with just familiarizing with one formula, you may. And you can also verify if this is correct, 3 and negative 4 on your own time. So again, this is how we illustrate 3 reflections of a certain point. Of course, the point here of graphing is to illustrate that our direction is good and correct. Thank you very much for watching.